The goal of this video is to explore the geometric interpretation of the span of a set of vectors. I actually want to begin by looking at an activity in your book, activity 2.3.2. Generally, I like to leave these activities for you to work through on your own or in class. But for this particular activity, it includes this really nice interactive set of visuals that I wanted to utilize. Um, let's take a look here. It first says to consider the vectors v equals 1, 2, and w equals -2, -4. And what this activity includes is this interactive visual where you have the opportunity to explore the span of this set of vectors by playing around with different linear combinations of them. And the way you do that is by making adjustments to these sliders labeled C and D. C in this case is the weight that we would put on the vector v when exploring linear combinations of v and w, and d is the weight on the vector w. And so as you adjust these sliders, a red vector is going to appear on the graph, which is the linear combination of v and w using the specified weights that you've given with c and d. And what you can see right now actually is there is a red vector. It is precisely the vector v because right now our weight c is set to 1 and our weight d is set to 0. So we are actually literally looking at the vector v here since we're looking at 1 times v plus 0 times w. But let's kind of play around with these and just make adjustments. If I keep d at 0, then you'll notice that all I'm getting are basically scalar multiples of v because we're again sort of scaling v in that way. If we start to make adjustments to d, and now we're looking at different weights for both of them, we actually still seem to be stuck on this same line. And I'll slide these around for a minute just so I can hopefully convince you that that's what's happening. So, hopefully you're seeing that we are sort of stuck on this line. There's nothing we can do. I encourage you to open your book and go to this activity, play around with these sliders. What you might notice actually is that v and w themselves are both kind of living on this same line. They are scalar multiples of each other. Namely, if you take v and multiply it by -2, scale it by -2, you get w. And so, one thing that's happening here is that the set of vectors that we can get to using linear combinations of these two vectors, aka the span of this set of vectors, is ultimately just going to be all vectors that are scalar multiples of either of these. So we basically geometrically will get a line in R2 as our span for these vectors. This activity includes all sorts of, specific questions, and I do encourage you to actually go through and try these out. I'm mostly using this for that interactive visual, but definitely try those other questions out. I want to come down here to part B, which kind of has us doing the same thing, but this time we have two different vectors. V is 2, 1, and W now is 1, 2. And so, same sort of sliders. This time you can see that v and w do not live on the same line, and we get a little bit more of an interesting behavior going on. As I adjust these sliders, you could see I can kind of go anywhere I want. And so if I were to sort of randomly, let's say, pick a point I wanted to get to, or pick a vector that I wanted to create, let's say I wanted to create the vector 2, -1. So I could kind of play around with these sliders. It's a little bit of sort of, playing around with these here. Let's see. Oh, that's pretty good. So to get to 2, -1, it looks like I would have to set the weight for this linear combination, the weight for v at, somewhere around 1.7, let's say, and the weight for w around negative, I don't know, 1.2 or -1.3. And those are, of course, just approximations, but The point here is that it does appear that I can get to that particular vector using a linear combination. So that vector is in the span, and it sort of feels like as you're playing around with these sliders that you can get anywhere you want in R2 by choosing the correct weight. And so we might say here that the span of these vectors is just all of R2 because we can take linear combinations of these vectors and get to any vector we want in all of R2. So big difference between these two examples here. The span of these vectors was sort of just a line in R2, whereas here the span was all of R2. And we could show both of those algebraically playing around with matrices. I'll show you kind of how that works in a little bit, but the main point here is kind of just the geometry. And again, this part of the activity includes other questions, and I do encourage you to play around and solve all these and answer all these questions. But certainly try this out yourself to maybe convince yourself of what I'm saying here. So again, the sort of goal of this was to convey the geometric meaning of span. We might think of the span as, this idea of walking in the plane, specifically R2. We can think of linear combinations of vectors v and w as a recipe for walking in the plane R2. We first move a prescribed amount in the direction of v, and then a prescribed amount in the direction of w. And the span consists of all the places we can walk to. A word on notation here. So we would denote the span of a set of vectors v1 through vn. Using this notation, we would write span, and then we use these curly brackets. That's sort of our set notation. So these curly brackets, and then we would list out those vectors. And so one thing we maybe started to get some intuition for and see in those, that activity in your book is that in R2, the span of two vectors can either be a line or all of R2. And those were the two examples we saw previously, and it turns out those are really the only two options. And so hopefully with enough examples, we can convince you that that is in fact true. Let's move to R3, another place where we could consider the geometry and really sort of visualize what's going on. So let's look at this example. Suppose we've got vectors u, v, and w. U is 1, 2, -1. V is 0, 1, 1, W is 1, 3, 0. Let's describe the span of these three vectors. And so what does that mean? That means, what vectors can we get to using linear combinations of these three vectors? And so, let's say we want to know, what vectors we can get to using linear combinations. We might set up an augmented matrix to solve a specific system. Let me set it up and then I'll talk about why this particular system makes sense. So what I'm going to put here are just the letters X, Y, and Z. And we're going to assume that this is a system where, maybe we'll call our weights C1, C2, and C3. So what we're looking at here are, what vectors X, Y, Z can we get to by taking C1 times U plus C2 times V plus C3 times W. And we want to know, which vectors X, Y, Z can we get to. When we're thinking about the geometry of these spans and kind of geometrically speaking in R3 or R2, we can talk about vectors as sort of arrows, but a lot of times we will kind of focus our attention on the end point of those vectors if they are drawn in that standard position starting at the origin. And that's kind of what we're going to do here. So I'm just going to row reduce this and kind of, go through the steps of row reduction and assume like sort of X, Y, and Z are just, real numbers, and we'll sort of see what happens. So if I'm row reducing this in an attempt to solve this system, we might start by doing R2 minus, I'd start by doing R2 minus 2R1 and R3 plus R1. Okay, and so 1, 0, 1, X, 2 minus 2 is 0, and then 1, and then 3 minus 2 is 1. Okay, and then what we'll see here actually is that I'm just gonna, walk through the arithmetic with these variables x, y, and z as I would with, as if they were numbers. So we're going to get r2 minus 2r1. That's going to say y minus 2x. And then negative 1 plus 1 is 0. 1 plus 0 is 1. 0 plus 1 is 1. And then this is going to be a z plus x. Okay, so we'll just keep going here. Next step might be to do r3 minus r2. And get 1, 0, 1, x, 0, 1, 1, y minus 2x. And then we get 0, 0, 0. And then we have a z plus 2x minus, these parentheses here, y minus 2x. And we are in reducer echelon form here, and this says that basically this particular system will only have solutions when what we have written here in this bottom row on the right hand side, this whole expression here, this system will only be consistent when that thing equals 0. If that is non-zero, then this is an inconsistent system. And so what we've sort of discovered here is that solutions to this will only exist when 0 equals, maybe I'll clean this up a little bit. We have a z plus 2x. Oh, sorry, that should have said plus x. Okay, let's just erase this whole thing and fix that up here. Made a little mistake, so that should have said z plus x, right? That was what was there earlier, and then minus y minus 2x. That's better. So again, that expression needs to equal 0. So we have a z plus x, and then we'll have a plus 2x. So that'll be a z plus 3x, and then we have a minus y. And so what we get here basically is that the only vectors, so a vector x, y, z is in the span of u, v, w only if 0 equals, maybe I'll do this in alphabetical order, 3x minus y plus z. So this is a relationship between those components of that vector x, y, z. We need 3x minus y plus z to equal 0. If we were to graph this in R3, graph all of the points, again, just sort of focusing on the endpoints of those vectors, all of the points that satisfy that, then we would end up getting a plane in R3. And I'll actually take a second here and show you that. So if we come over here to our online grapher, so we want to graph 0 equals 3x minus y plus z. So 0 equals 3x minus y plus z. And I'm using Desmos 3D here, which is a really nice user-friendly online grapher for three-dimensional things. I love Desmos, the regular Desmos for 2D, but little plug for Desmos 3D. And you can see when I put that expression in here, we get a plane in 3 dimensions. And if you've taken a Calc 3, like a multivariable calculus, then hopefully this is something that you explored at great length in a class like that. If you haven't, then that's okay. We're going to be exploring geometry in 3D here. And there's not too many different objects we're going to be looking at in this class. Planes are certainly one of them. And so this is an example of a plane. And so all of the vectors that start at the origin and have their endpoints on this plane are going to be in the span of those vectors, are going to be linear combinations of the of the vectors that we saw in this example. Let's do another example. So new vectors here, 2, 1, 3, negative 1, 1, 1, and 1, 2, 1. Let's go ahead and I play that same game. We want to describe the span. So I want to row reduce 2, 1, 3, negative 1, 1, 1, 1, 2, 1, and then just sort of a general vector x, y, z, because I want to see if there's some relationship between x, y, and z. And interchange here. And then we could do an R2 minus a 2R1 and an R3 minus a 3R1. We'll get 0, minus 1 minus 2 is minus 3, 1 minus 4 is minus 3, and then we'll have an x minus 2y, and then 3 minus 3 is 0, 1 minus 3 is negative 2, 1 minus 6 is negative 5, and then we'll have a z minus 3y. Okay, we might do R2 divided by negative 3, scale that. So we get 0, 1, 1, and then x minus 2y divided by negative 3. Okay, and then maybe we'll do I'm just going to do one more step here because it shows off what I want to show off. So R3 plus 2R2. And to get this to sort of the full reduced row echelon form would get pretty messy, and I don't think it's necessary for what I want to show. And then x minus 2y divided by negative 3, and then this is going to be a 0. Negative 2 plus 2 is 0. Negative 5 plus 2 is a negative 3. And then we have a z minus 3y, and then plus 2 times x minus 2y divided by negative 3. So you can see that's pretty messy. What we might notice at this point actually is that this system is ultimately going to be consistent. We're not going to get a row of zeros. And so, there's the same thing that happened in the previous example. I can just jump back there and remind you sort of what happened here. When we reduced this, we got this sort of row of zeros on the left. And so that sort of prescribed this relationship between x, y, and z in order for this system to be consistent. The same thing is not going to happen here. We could continue to row reduce, and we'd ultimately get no row of zeros in this portion, in this sort of coefficient matrix portion. And so that's enough for us to say that this is fully consistent. And that tells me that basically any values of x, y, and z will lead to a solution. If we wanted to sort of discover specifically what that solution would be, we might keep going with this. And then, you could tell me what x, y, and z are, and I could figure out what C1, C2, and C3 are in order to get that particular linear combination. But this is going to get really ugly in general. If you ever wanted to do that, I would recommend, just sort of, setting X, Y, and Z to those specific numbers, and then we're reducing. What we're trying to do here is just show that, essentially we can get to anything we want. So we would say that the span of U, V, and W in this case is all of R3, is anything in the the entire three-dimensional plane there, or three-dimensional space. One more example in R3. So let's do this example. So same game, 2, 4, 6, negative 1, negative 2, negative 3. And again, x, y, z. So we'll do an R2 minus a 2R1. Okay, so 2 minus 2 is 0, 4 minus 2 is 0, negative 2 minus 2 times negative 1 would be negative 2 plus 2 is 0. And so we get y minus 2x, and then 3 minus 3 is 0, 6 minus 6 is 0, negative 3 plus 3 is 0, and this is a z minus 3x. And we're already in reduced for echelon form, and what we have actually is the fact that, in order to have a consistent system, we need y minus 2x to equal 0 and z minus 3x to equal 0. And so we have essentially an x can be anything we want, and then we would get a specific y and z. And so ultimately what we've got here is a set of points that are all going to fall on the same line. What you might have noticed is that the original three vectors were all actually scalar multiples of each other. And so any vector that is a linear combination of them is going to also be a scalar multiple. And so, you could pick an x. Let's let x equal, 3. Then we'd find that y is equal to 2x from that equation there. So we'd have that y equals 6 and z is equal to 3x. So z would equal 9. And so the vector 3, 6, 9 is a linear combination of our original vectors. It is also a scalar multiple of all three of those vectors. And so that's going to always happen. And again, this gives us a line in R3. So the span of U, V, and W is a line in R3. Specifically, it is the line that is scalar multiples of U. So basically, or V or W, but I'll just take U for kind of simplicity here. So we scale that vector U, 1, 2, 3, and we get to all points in this span, which would give us a line. So to summarize, and I should go back. So kind of what happened in each of these situations in terms of pivot positions. In this first example, we had 2 pivots. I'll just sort of write that up here. So 2 pivots, right? So pivot. In this example here, we had 3 pivots, right? So boom, boom, boom. We didn't go all the way to reduce or echelon form, but that's where they would be. In this example here, we had 1 pivot there. And so this sort of summarizes those situations in R3. If we have 1 pivot, then the span is a line, and we just saw that in that example just now. 2 pivots give us the span as a plane. That was the first example. And 3 pivots, the span is all of R3. And those are going to be the only 3 possibilities for the geometry of the span of a set of vectors in R3. Okay, so kind of summarizing some of this a bit more and generalizing this a bit more. Suppose we have vectors v1 through vn in Rm, then the span of those vectors equals Rm if and only if the matrix, whose columns are v1 through vn, has a pivot position in every row. So at least m vectors are needed if we are to have a set of vectors whose span is all of Rm. We think of linear combinations of a set of vectors as the result of walking a certain distance in the direction of v1, followed by walking a certain distance in the direction of v2, and so on. And so if the span of a set of vectors is Rm, then we can walk to every point in Rm using the directions given by the vectors. To reach every point in Rm, this proposition is essentially saying that we need at least m directions in order to have enough flexibility. So if we want to have a set of vectors whose span is R2, then we need at least 2. If we want to span all of R3, we need at least 3 vectors. If we want to span all of R5, we need at least 5. If we want to span all of R100, we need at least 100 vectors. You could have potentially more than that, but if you have less than that, then there's no way you're going to span that entire space. And one more point here on some terminology. Because span is associated with a set of vectors, we always want to make sure we're saying that we're talking about the span of a set of vectors. We don't want to talk about the span of a matrix, although oftentimes we will be talking about spanning in matrices, but really what we're talking about is the span of the columns of the matrix. And I will hopefully, use this all correctly, but it's definitely something that is easy to make a mistake with. So just try and be careful with that.